Hi class, we were going to do an example of how to do calculations of torques on current loops. So let me give you an example problem and we'll just kind of walk through that together. So this is kind of a classic kind of problem you see. It's similar to the ones that you see on homework. In this case, we're going to do an example with a rectangular loop. In homework, I think I gave you a circular loop. You apply all the same reasoning to circular loops versus rectangular loops, especially the way we're doing them, because we're always looking for the maximum torque that you experience on a loop. If you encounter a problem where you're not looking for the maximum torque, you can still work things out, but only in cases where you have a highly symmetric loop where you can always work out directly what the force on the individual sides of the loop are. If you have something like a circular loop that's inclined to a magnetic field, it becomes a little more difficult because in order to properly do that, you'd have to use an integral, which we haven't been doing, of course. But this should be very typical of the kinds of problems that I expect you to be able to do. So imagine you have a rectangular coil. It has 200 turns, so it's a whole bunch of stacked loops together acting as a single loop. It's 5 centimeters wide by 4 centimeters wide. It's placed in a magnetic field of a certain strength, 0.35 teslas in this case, and it experiences a torque, 0.22 Newton meters. And what we want to know is, given that torque, what is the current that must be running in the coil? Now I will remind you here at the outset that one of the things that we often stumble on is that the units of torque are Newton meters, and Newton meters in this case are not the same Newton meters that we encounter when we talk about work and energy. Okay, so you will recall that Newton meters are joules, but this is Newton meters which are not joules. These are Newton meters. We leave them at that because we're talking about torque, not about a scalar, not about energy or work. Okay, so if you don't remember that from first term, do not be tempted in this case. Okay, so let's go ahead and work that problem out. So I always like to draw a picture, of course. So I have a square loop. Okay, and the sides are 4 centimeters, which are 0.04 meters, and 5 centimeters, which is 0.05 meters. Okay, it's immersed in a magnetic field. Okay, and that magnetic field can point any direction. The problem didn't specify because in principle doesn't matter, but we're looking for the maximum case. So let's imagine that the magnetic field points like this. Okay, and that magnetic field has a value of 0.35 teslas. Okay, so the torque, the maximum torque on a current loop is given by the number of loops, number of coils in the loop, times I times B, the current that flows in the loop, the thing that we're interested in finding, times the magnitude of the magnetic field that the loop is immersed in, times the area of the loop. Okay, so one of the things I always like to do when I'm doing problems, particularly when I'm just starting from formulas like this, is take an inventory of what I know and what I don't know, because that tells me whether or not I need to go looking for another formula or something else to work with. So in this case, torque, we're given that, okay, we're told that, so we're told that the torque in the problem is 0.22 Newton meters, so I know that. We're told the number of coils. The number of coils we're told in the problem is 200 turns. The current, that's the thing that we're interested in finding out. Okay, so that's definitely what we're after. We're told the magnetic field value, and we're told enough information to figure out the area of the loop. It's 0.05 meters times 0.04 meters. So I'm going to go ahead and check that off as well. Okay, so this is perfect. I have a single equation. I have one unknown, so I don't need to go to any other formulas to figure anything out. There will be problems like this where you do have to figure things out. Maybe you have to go work out forces and then compute torques with those forces. Maybe you'll have to work out the magnetic field first. Who knows? In this case, this problem is relatively straightforward. It's a single equation, and so you can solve algebraically for what you need to find. Okay, so let's go ahead and do that. So the current, which is what we're interested in, is equal to the torque divided by the total number of turns times the magnitude of the magnetic field times the area of the loop. And so if I want to write it explicitly in terms of the things that I do know, I will write N times B times the length of side 1 times the length of side 2. And those two things give me the value of the area. Okay, so at this point, it's just plug and chug in terms of the numbers. I know what the values are. So if I were to put those all in, so this is 0.22 Newton meters. It's 200 turns. Okay, there are no units associated with this. The magnetic field is 0.35 Teslas. And the side of length 1 is 0.05 meters. The side of length 2 is 0.04 meters. And if you put that all into your calculator, then you will come out with the current is 1.6 amps. Okay? Now, I'm kind of playing fast and loose here by going directly from units that are newtons, meters, Teslas, meters here, directly to amps. Okay? In this case, you could go back. You could expand all the quantities that go into newtons, all the quantities that define and relate Teslas to ensure that you come out with amps. In this case, the reason I'm playing it fast and loose is because I'm confident, because I'm working in pure SI units, I'm working in newtons and meters, I got rid of my centimeters early on, that the answer is going to come out in the correct SI unit. But this is a good exercise for you. You should go in and put in those substitutions and confirm for yourself that indeed you do get amps out at the end. Okay, so that's a good example of a torque problem. I hope it helps you out. If you have questions, you know where to find me, and we'll do some more physics sometime. Talk to you later.